Ready to get started?
Not on like a regular basis.
Here we go. We are where are we? Right here? Finishing chapter 6 today.
She's Han Solo now. I'm
All right.
Yeah.
And then quiz on Thursday, correct?
That's hilarious.
Quiz on Thursday. Open book, open note, right? Assigned seating, just so you've been warned. I believe in the concept of letting you know in advance so you can emotionally prepare. Because I know some people are stressed out about tests, and then also they find out the last second is the assigned seating, and they think it just adds so much to their stress there's no way they're going to pass. So I let you know in advance. Well, now you know. But now you know there's going to be assigned seating for the next quiz, right? Okay. All right. I want to talk about right here. Okay. This is your chapter participation. At the same time, I'm preparing you for your quiz in 2 days. Transportation, assignment, and transshipment all have nodes. And every one of those nodes represent what? No, but good, I appreciate, yes, good recover. Constraints. And every one of these, transportation, assignment, and transshipment, have arcs. And every one of the arcs represent what?
Variable.
All right, look at that. I can hear you. With the fan on and everything. What else I want to remind you of? They have so much in common, I can't remember. What is it when if you had to draw a network for any one of these three, there's something you got to put on the outside of the left-hand node. In most cases, what would that be called?
Demand.
No, on the left-hand node.
Oh.
Supply.
Very good. But on the right-hand node, that'd be the demand, right? Now, don't get me wrong. If you get them backwards, I'm not taking any points off as long as the numbers all make sense. You know, and the arrows are going from right to left, then that's fine. If you want to do it backwards, but most commonly it's going from left to right. Running out of things to remember, but the reason I'm refreshing your memory is because there's 2 more from this chapter, and there's a lot of similarities, and where I want you to really keep track on your notes, I'm going to really emphasize when we get to what the differences are, because I'll point out the similarities, and I'm really going to emphasize the differences. And I want to make sure you recognize problems when you read them. So I posted an answer from every distribution and network model. There's 5 answers posted for you to use to study from, 1 from each kind. So what I'm suggesting is you go to Blackboard, you see the numbers I listed for the answers. They're on the names of each one. Attempt to look at the problem and try to say to yourself, okay, is this transportation, is this assignment, is this transshipment, is this shortest route, or is this max flow? You have 5 of them, really only 4, because it'll be obvious what the 5th one is. But and see how well, if you feel confident that you're getting those the first 4 right, then you may be semi-prepared for this. Because actually, a lot of students, that's where they have trouble. And even though you may be thinking you're answering an assignment problem, it could be a transportation or vice versa, which you're going to still get a lot of points because there's so many similarities, but it's not going to be correct. Recognizing what kind of problem is the first step. You got to really make sure you understand to be prepared in 2 days. And then, if you recognize as a transshipment, there's something specific you're looking for to recognize as a transshipment. What makes that one different? That's right. That something's being shipped to somewhere that then continues on to somewhere else. That's the hint that will make transshipment kind of jump out of you. And when you first start reading it, you're going to go, wow, this is transportation. And you got to, the key, you got to pull into your imagination. You just got to start saying, I'm going to imagine this is a real, that I'm managing this, and visualize how this is going to work. And also you'll go, oh, it's being shipped somewhere, that's then going on to somewhere else. You'll go, oh, this is transshipment, and then you'll start putting it all together. The middle nodes on transshipment are always less than equal, greater than equal, or equal to what?
0.
But what? Equal. Thank you. Okay. I don't know why you're not switching me. I'm talking about chapter 4. Oh. Okay, you ready? Here we go. Shortest route, max flow. The nodes are the same rule, but they all represent constraints. Every node is a constraint. The arcs, the same rule. Every arc's a variable. Right? I've said that for all 5 of these, right? here is what makes shortest route kind of freaky for some people and makes it different. Ready? The story's going to go blah, 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 blah. And you're given a network to look at, which, by the way, that example problem, one of them is shortest route, and it's all about the picture. You've got to learn to be able to recognize this, and here's the deal, here's the rule. Any arc between two middle nodes goes both ways and represents two variables. Figure that? Any arc between two middle nodes goes both ways and is really two variables, unless there's an arrow pointing that it's one way. You have to assume two ways, unless you see something that's indicating it's a one way. So, for example, look at arc G. X is the variable, but there's two variables and they have numbers. X what?
3, 5, and 5,
And
3.
X what?
5, 3.
There they are. 3, 5, and 5, 3. And what you're doing is you're saying, okay, if that arc between two middle nodes, if there's an end or a beginning node involved, it's a one-way, period. Let me say that again. If the first node or the ending nodes involved, the arcs that are touching those are one way. These are one way out, and these are one way in. Right? But every arc in the middle is assumed to be two-way unless there's an arrow involved. Look at arc B. How many variables?
1.
Well, what's the variable? X? That's right. And the reason it's only one variable is because it's leaving one. And it's only a one way. It does not come back. Nothing comes back to the beginning. Things could go here, 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 then here, but it will never come back here. What's it leave? And once it gets to here, it's done. It can't go back. That's why these are one way and these are one way. So, if there's a question you might have when you look at something like this, especially first route, it may say, how many variables total? And that, that's a little bit of a challenge, because you got to go, well, 1, 2, 3, 4, 5, correct? Then you got to go, and I always had to put my hand there and kind of go, yeah, count these already. And what was that, 5? 6, 7. What's this one? 1 or 2?
1.
One way. What was that? 8. I already did this one, 9, 10, right? 11, 12. You gotta remember what I did here. I guess all that's left now is this. 13, 14, 15.
3 and 4.
I don't know. I see 15. That's how hard it is. I gotta sit there and mark them even, mark them all. So you see how I went both ways when I figured out that the arc was between two middle nodes, meaning two variables, when I got to the end. All right. I want to review this real quick. What are the constraints for nodes that represent supply, the equality, less than equal, greater than equal, or equal, in almost all cases, not all, but in most cases.
Less than equal.
Less than equal. What about for demand?
Equal. Equal.
Equal. Assignment problem. The agents, which would be the demand on the left, less than equal, greater than equal, or equal?
Equal.
Less than equal. Less than equal. The
Oh,
demand,
yeah.
the supply, the agents are less. But the demand, the jobs that have to be filled, they're
Equal.
The middle nodes on transshipment are less than equal, greater than equal, or equal. Equal, and then you told me earlier it's equal to what? Zero. The supply nodes on transshipment are less than equal, greater than equal, or equal?
Less than equal.
Less than equal. And then the end customers nodes are less than equal, greater than equal, or equal?
Equal.
You got it. Okay. Now, you ready? Now that that's all been reviewed, in shortest route, every one of the nodes are equal. Figure that? They're all equal. In shortest route, the beginning node constraint is always equal to 1. The ending node constraint is always equal to 1. And every one of the other middle nodes constraints are always equal to 0. Get that? That is different than the other three, so I'll make sure you hear that again. You know in transshipment how the middle nodes are equal to 0 because everything that comes in goes out? In shortest route, everything that goes in goes out, just like that. So every one of the middle nodes, when you write those constraints, are equal to 0. But the beginning and the end, those constraints are equal to 1. Okay, you ready? Transshipment, everything that goes in the middle heads back out. And when you write that constraint, if you recall, I said you either have to use a positive variables on the way in and use the opposite on the way out, and you have to be consistent between the middle nodes. Does that sound familiar?
Yes.
Same rule here. Once you pick one of these middle nodes, and a lot of people, after they do node 1, they go to node 2, and there's a middle one. They'll make it equal to 0. And you're going to decide the arcs going in are either going to be positive or negative, and the arcs going out are going to be the opposite. And whatever you decide on that first middle node, when you write that constraint, you must have consistency on every middle node, just like that transshipment. You have to have consistency on those middle nodes. You can decide, let me do this one. I'm going to show you every arc coming in, I'm going to make negative. Every arc going out, I'm going to make positive. And then I'm going to make it equal to, help me out, 0. So there's only one point. Make sure. No one heard that. Negative x12 minus x52 plus x25 plus x26 equals 0. Now that I made the ones coming into 2 negative, I got to make the ones coming into any of the negative, middle nodes negative. I got to stay consistent. Now, just for hypothetical, I'm going to pick another middle node, but I'm going to switch to positive on the way in, negative on the way out, just to make sure everybody sees how another way it's done. I want to go with this hard one. You ready? Everything going in, I'm going to make positive. Everything going out, negative. And this is going to be equal to what when I get done?
0.
Okay. We're all together. Here we go. X13 plus X53 plus X43, I got to stare, minus X35 minus X34 minus X36 equals 0. And then that now every middle node, because I made the ones going out negative, I got to stay consistent and make the ones going out negative. How do we feel? Okay, now I'm going to put a story to it. Now you got all the little rules down. That should make it easier. If you just look at those rules and go, okay, I'm going to draw. There's 6 places. Where it starts, where it ends, it got to be equal to 1. And all the middle places. So here's an example story. An employee has got to get to a conference. You have to make sure she gets to the conference at the least expensive possible way. By the way, in real life, a lot of, again, logistics coordinators will use this to make sure the trucks, they know exactly what, this is one of them, as well as that transportation model. Logistics people are planning at exactly what the route will be, how the truck is loaded, so that the truck is loaded that the last drop-off is at the front and the first drop-off at the back. They're also using this model here to tell the drivers exactly the route they should be taking and keep the cost of gas as low as possible. That's what this does. It figures out the exact route. Now in this case, it's not just a truck going and delivering things. We got gas and wear and tear and stuff and a driver. This is an employee that's got to get to a conference, and your task is to get her to the conference as least expensive as possible. But you've got to take into consideration her time. Because as she's traveling on the, whatever form you decide to make her travel on, we have to pay her $15 an hour during the time she's traveling. All right? As well as the cost of whatever the ticket is in the form of transportation and the time. So, you looked up every possible way to get from, where is she starting from? Paducah? That's where it's at. Where's she coming from? Lewisburg. Got to get from Lewisburg to Paducah. You happen to be on human resources, or where I work, the people who conduct, schedule all the travel. I worked for that consulting firm where there was like 90 of us flying out every 3 days. So, we had like 5 people all day long figuring out everybody's schedules, figuring out what the flights are, booking the flights, securing the rental cars, securing the hotels. It was a whole job. It was not just for one person, like 3 people. In this case, this is the kind of thing that you would use to plan this out. If you like this kind of stuff, person from Lewisburg to Paducah, and you look up every form of transportation available, and how long it would take, and where it would go to, all the possible stops along the way. And you came up with, let me get here, all of these possible different forms of transportation, and here are all the different stops if that form of transportation were taken. For example, let's start with Route A. If you decide to put her on a train for a 4-hour ride, does it get her to the end? Isn't that it? The train is Route A. Does it get her to the end to Paducah? It doesn't. So there's more to it. Then you gotta go, well, what's in front of her now? It could be F, it could be K, so go down here. Well, after she gets off the train, she's gonna have to get on a bus for 3 hours. Or, what was the other letter?
K.
A? No.
K.
K.
Thank you, K. A taxi for how long? 3.5 hours. This doesn't. I mean, I don't know if you guys have taken taxis, but I've never gotten out of a taxi for, it could be 5-minute ride and 20 bucks. So, there you go. Here's all the different possibilities. Here's where it will take her, based on the letter, you look at the kind of the drawing there, and on shortest route, you're given the drawing, you're given the information, you gotta come up with the objective functioning constraint. Where every one of these lines are, where those letters are, this is gonna be the total cost if this route were taken. Now this total cost isn't just that ticket for the train or the bus. You gotta add your time. So we're looking at, I can't remember how many hours that one was.
4.
4 times, we got 4 hours, so there's a cost of $20 for the ticket, plus 4 times $15. That was, I know that's what I said, I couldn't remember that was correct. Let's jump down, what was that train, bus here. Bus, 3 hours, $15 for the ticket, 3 hours times $15. And then you may have another thing. So you jump right to here. You take all those tickets and take each amount of time times the $15, add together. Now every ARC's cost has been calculated. To save time on a quiz, it's possible, not necessarily final, but it's possible, you would just be given this. You won't even have to do this calculation. But in real life, it's the total cost if this were selected. Not just the cost of the ticket, but the upper time. And the cost of time, you can see, is in most cases a lot more expensive than the ticket, which means time could be of the essence for selecting which one to go. I got these coming up. Uh-oh. Not just one. Oh, all right. So, you now put, hang on. You ready? You now put those totals on every arc. In the other 3 models from when did we last see each other? Thursday. When were these costs used? In the constraint or the objective function or where?
Objective function.
Only the objective function. On every one of those 3, correct? Same goes for here. Shortest route, those costs that are on the arcs are only in the objective function, not the constraints. So that's 4 out of the 5 models that you're going to blow it if you put any of those costs in the objective function. They're only in, in the constraints. They're only in the objective function, not in constraints. Until you get to the last model. Do not include this point on what we just said. The other 4, all the costs on the arcs, or the numbers, are part of the objective function only, not the constraints. Until you get the max flow. Okay? Same with this one. So, but you don't need those costs to do a constraint. And to make sure you're with me, we're going to do this constraint right here. How many variables?
5.
5. All you got to do is count any arcs touching the node you're about to write a constraint for. You see 5 arcs touching it on any of the sides, that's how many variables you're going to have. Are the variables going to be positive or negative? It doesn't matter. I mean, do you have to make that decision?
No.
You don't, because I said at the end, the constraint always has what kind of variable? Positive or negative?
Positive.
Positive. At the beginning, this constraint always has what kind of variable? Positive or negative? No.
Positive.
That's what's weird about it. They're all positive in the beginning, They're all positive at the end, but the middles have the negative with the positive, but only the middle. And it's been that way, it's that way with transshipment, when you first get into negative variables. It's the same way, same rule. The middle ones have positive and negative, but the demand are all positive variables, and the supply are all positive variables. It's not till we get to max flow that all these rules I'm telling you are out the window. It's just for those first four that all these rules are applying. They're all very so similar to each other. That's why you gotta recognize, hey, is that shortest route or is that max flow? Because there's a whole different set of rules in this max flow compared to shortest route. Help me with this constraint. Ready? Hit me with the numbers, with the smallest number first, so we're all on the same page. The variable x, 1, 6. Plus x,
2, 6.
2, 6. Plus x,
4, 6.
no,
3,
number.
6.
3, 6. Plus x,
4, 6.
4, 6. Plus x,
5, 6.
equals 1. That's it. Exactly. Okay? That's that constraint. You can do any of these constraints, right? Like x12 plus x15 plus x13 plus x16 plus x14. You can do them in any order. I only want you to do them numerical order so we're all saying the same thing. Equals 1. Plus and minus, these are all equal to 0. You can write those out. The objective function is just like the other three models. You just take every variable and put it with the number of the cost and add them all together. Now, remember the story. We're trying to get her to this conference. Is this a minimize or a maximize?
Minimize.
Minimize. Let's do a couple of variables. I got to get some costs here. I want the cost. Remember the cost for A. Remember the cost for B. Remember the cost for C. Ready? A, 20. No, I'm sorry. 80, 130, 40. Okay, ready? Let's do, we're doing the objective function, min 80 times x, 1, 2, plus 130 times x, 1, 5, plus 40 times x, 1, 3. Just like all the other ones. Exactly. You just take the cost, total cost, put it in front of the variable, you're adding them together. Now, I want to keep going. Hang on, I almost forgot. We got to get it both way here. Is H both way? H. Okay. What's the cost on H? Oh, shoot. We got to get here. 30. Ready? With H, it's going to be 30x 3,4 plus 30x 4,3. This goes both ways. It's two variables. They're both represented by the same exact cost, but she could be coming from here going here, or could be coming from here going here before going there. It's a two-way. So you've got to include both variables in the objective function. Let's grab a cost for, let me see here. F. Help me out with F. What was F? Let's see, 60. So what do we have here? 60, then what? X what? 25 plus 60x. You got it. That's the weird part about shortest route is those middle arcs have to be assumed to go both ways unless they're there. All right, so we write all of our objective function with all the variables. What was that? 2, 5. Where's my 2, 5? There's the 62, 5. So it's got to be a 5, 2. There's the 5, 2. What was the other one? 3, 4. 33, 4. 34, 3. All the arcs that are in the middle, between middle nodes, you'll see up there twice with the same number. All right? And here's our constraint. At the beginning, equal to 1, all positive variables. At the end, equal to 1, all positive variables. Looks like the ones going in are negative in this example, and the ones going out are positive. Negative x12, negative x52, plus x25, plus x26 equals 0. You can put them in any order, it doesn't matter. And if I were entering this on Excel, I have all my variables. I have an x25, I have an x52, I got an x34, I got an x43. And in the objective function, I'm typing in all these numbers. And on the constraints, I'm putting a 1 underneath that variable, a 1, a 1, a 1, a 1, a negative 1, a positive 1, a negative 1. And you're just putting 1. And you're using the same Excel spreadsheet, the same Excel, there's nothing different about this one that you've already done in the several examples before this, solving them using Excel, same thing, except for here, there's so many variables that look like this big. That's the only reason. We only have 6 constraints. Here's the objective function because of all the variables. Here's the optimal solution. What's going to appear here? What is these numbers going to turn into? They're either going to be zeros or ones. Any place there's a 1, that's the one you should be choosing for the route to take for her to make it to the conference. Down here, all of these are just like all the ones we've had before this. This is constraint 1, so it's taking the optimal solution times that 1. Plus optimal solution times that 1. Plus optimal, and just adding these all together is the formula right there. Right here is the optimal solution times the negative 1. Optimal times the 0. If you have to use Excel, I would open this up, and if I click on this cell, you can go, oh, okay, you can see what's going on here. 6, 16, 6, 16, 6, 16. You can see that. And what about the objective function? It's just like you expect. This times this, plus this times this, plus this times this. So it's going to be 12 and 16. 12, 16, 12, 16, 12, 16. Just like you've seen. Just have more variables. Okay, here we go. I'm going to solve this, and you're going to tell me the route you're going to center on. Here, the solver. Let's see. Objective function should be E18. This is a min. My answers are going to be from, what is that? E16 all the way to U16. Did I say U? E to U. Okay. All the constraints are equal. You can group them all together. They're all equal signs, so we're going to go from E22 all the way to E27, and wherever the numbers are. E22, is that B? B22 to B27 are over here. What about all the variables are non-negative? Yes. So we're using sequence LP, linear programming model? Yes. Solved. Okay, she's starting out in Louisville, and then following what route? From node 1 to node 1? 3. That's going back to 1. Okay, hang on. We gotta get my node here. Node 1 to node 3 is what route letter? C. So C says she's taking a bus. For how long? 2 hours. We paid her $30. We've got the ticket for 10. We're at $40 so far. All right, let me go back here. Then from when she gets there, where does she go? From 3 to what? 3 to 4. She went from 1 to 3, 3 to 4. And that's going to be, what about that is? 3 to 4 is what letter? H. So H is going to be taking a taxi for an hour. It's all cheap at 15. I don't even know how. So
He was probably
$30
looking at that
total, right? And then let's see what's that. When she gets out of 1 to 3, 3 to 4, then where?
And then that's gonna be
4 to 5. 4 to 5 is what letter? I. Is that I? She's taking a train for 2 1/3 hours. Wow. What was the first mode of transportation? A taxi? What was the before taxi? A bus, then a taxi, then a train. If it saves us money, so be it, right? Okay? And that took us to what node? 5, and then from 5 to 6, obviously, right? Which would be what route here? 5 to 6 is what letter? L. Wow. She is then taking another trip for an hour, 1 1/3 hours. The ticket's her time is 20. Or 1 1/3, I get it. And $10 for the ticket, $30. My question for you is, how much is the least expensive way we can get her to this conference? 150. This is the output if we were to use the software. All those variables, the values would either be 0 or 1. You look where the ones are, and you look to see what the route is, 1 to 3, 3 to 4, 4 to 5, 5 to 6. And there's the total, whatever we're trying to minimize or maximize, in this case, the total cost to get it with. And there may be an alternative, not always, but there may be an alternative way to get her there, but it won't be any less than 150. That is the lowest we can get. So we might as well just send her this way right here, instead of spending all that time trying to figure out if there's an alternative way. Even if there is, it will not save you any money. That's the lowest it can get. Just forgot. Yeah, or not yesterday, Thursday, on assignment, I said sometimes there's less people or agents to assign to a task. And I said you had to do something if you run into that situation or it won't be solvable.
You have another one.
You have to add a dummy agent. Now I'm gonna run down, again, I wanna go to assignment, make sure you understand what I'm saying. Right here. If we only had 2 notes here and 3 notes here, or the story said we have to assign these 2 employees, but we got 3 projects to assign them to, it's unsolvable unless you add a dummy agent. You have to have the same amount or more on the left and the right when it comes to assignment problems. Transportation is the one has a very similar situation. I think I forgot to mention it during the lecture. So let me show you transportation, very similar, and this is the one I forgot to mention. If you add up these supplies, and it's not enough to cover the total demand, you also have to add a dummy supply with the amount to make sure there's enough to cover. Whatever the assignment is to that dummy, that's the customer you gotta get a hold of and say, I'm sorry, I'm backward. It will decide who to put on backward by adding this, if the supply does not equal demand, if it's too short. If you can have more supply, that's why we make these less than equal. But let's say this is a 20, and that's a 20, that's 40, and this is 20, 20, 20, 60, it's unsolvable. You gotta add a third, and you gotta put that other 20 out here. But it's ours. Each one, if you're running that constraint with that node right there, and you've got 3 more variables whose costs are, have to be so high that it would never be selected. It's going to show you the cheapest way to get these 2 and which customers will get goods from these 2 locations. But this third one, you purposely make the cost so high so it will never get selected, but it will assign those 20 to somewhere, and that's the customer you got to say, I'm sorry, that 20's on backward, because you don't have enough supply. So I forgot to mention that. One issue you got. Your class I mentioned. All right, we got one more. Right? Was it 150 on the PowerPoint? Okay, max flow, maximal flow. Right, let's take a look at it. We'll get the story. All right. I love this example. This is real. It's real. You know those delivery, FedEx, UPS, all those next day delivery companies who are using planes. If you go by Mission Airport at night, most of the planes you're seeing kind of off the side are the FedEx. They're not even at the terminal. They're off to the side over there with the private plane. And they're doing their deliveries. The companies are so adamant about keeping their reputation and taking care of the customer that they all plan in advance what will happen if a plane goes down. The party still goes on, but deliveries have to be made. And they got to figure out a way to get those packages to their point to where they need to be, an alternative plan in case any one of the planes go down at any time. They have this all in place. They know exactly what to do if this happens. And it happens. Oh, I had no point to interrupt my lecture. Darn. All right. Here's an example. Now, we're going to pretend we're in San Diego. And there's this plane. We have 3 planes that head out from San Diego taking packages to our other hubs. One's going to Denver, one's going to Dallas, and one's going to Houston. And if this plane goes down, we got to make sure that there's excess capacity on these other planes to still get the packages to the places they need to be. This is trying to figure out what's the most that, if this plane were to go down, what's the most cubic, I think it's square cubic something space available, 4,000, 3,000, when we get to the end. What's the most that could make it there, no matter where it's coming from? So we can see if there's enough spare capacity, because usually we have, on average, 5,000 cubic feet shipped here on a nightly basis. Everybody hear that? 5,000. So this has to be 5,000 or more when we get to the end. All right. This is weird, I know. Hang on. You ready? Every node is a constraint just like the other four. But every node equals 0, period. Everybody hear it? What? You know what? I'm not having a second thought. Yes. Every node every constraint is a node, and every constraint equals 0 in max flow. First time you've seen this. In max flow, you'll always have the arrows. You don't have to assume the both ways like shortest route. Only in shortest route is that case. You'll have arrows. You won't always have them going both ways. Look at between Atlanta and Houston. We do not have a plane going from Atlanta to Houston, only from Houston to Atlanta. All right? And even if it's going the same route, two different directions, it doesn't mean it has the same number like shortest route does. Because in this case, this plane usually takes 6,000 cubic feet maybe, but it has capacity for 9,000. So on average, it has spare capacity of 3,000 that could take some other packages if a plane goes down. But the plane that comes from Dallas to Houston, it carries even less packages, so it has 5,000 spare capacity. And that's what the numbers are doing, because the routes have taking different packages on average. So on average, those numbers represent the spare space available on the plane that are usually on average taking these routes. And the planes will always go on the same route. So this is all about the fact. So let's get to the story. Oh wait, one more rule. Every arc's a variable, just like all the other ones. But this is the only one that you have to add an arc to. That's your, matter of fact, put max flow, step 1, add an arc. You've got to make that your first step so you don't forget it. The added arc is going from whichever the end node is, in this case it would be 7. And it's going all the way back to the beginning. It's not a real route. It's how max flow is able to figure out the maximum amount that could go out of Tampa. So you're looking at, even though they're coming from 3 different directions, what amount lands here? And the only way to find out how much lands there is you've got to add a variable going back to the beginning. That variable is the amount that could maximize through this system. Let me tell you a common way this is used that I've seen it used in a lot of different places. Big cities, when they're about to shut down a part of a highway or a road, they go through this to figure out the amount. They know exactly the average amount of cars that go through that path. And they got to come up with the alternative routes for the cars, and they got to make sure that the amount of cars that go through that will make it to the other end when they get through their detours. And that's this exact thing is used in those situations. Probably even a smaller town as Flint is. How are we doing? Good? You ready? This is the only one that all of these numbers are not in the objective function. Everybody hear that? Matter of fact, none of these are in the objective function. This is the weirdest objective function of any of them. This one in a lot of aspects. But the objective function is one variable. And that variable represents the arc you drew and added to it. So in this case, and almost every time, this is all about what's the most you can get to the endpoint. What's the most? That's why it's called max flow. So your objective function almost always is max. X, whatever the numbers represent the arc you added from the end to the beginning. So what 2 numbers would be here?
7, 1.
That's right. If this had 8 nodes, it'd be 8, 1. If it had 9 nodes, it'd be 9, 1. If it had 5 nodes, it'd be 5, 1. It's from the end back to the beginning is what's got to be represented in your objective function, and that is your full objective function. Look how different that is from the other 4. So how do you, by the way, the constraints are just like the other one. You do not use these numbers in the constraints for the nodes. The node constraints do not use those numbers, just like all the other models we've learned. But this is the only one that you've got to write a separate constraint for every arc that, except for the one you drew, because it's in the objective function. You ready? I want to make sure you see the difference. So I'm going to let's grab this node right here and write this constraint. First of all, if you look at your rules, I said every node is either less than, greater than, or equal to something.
Equal to 0.
Zero.
Okay, so I'm going to make this one equal to 0, and I know I'm right because it's a node, and every node is equal to 0. Now, how many variables are going to be in this? 3. Long.
Wait,
4,
which
because
one?
you've got to add 1.
Node 1. How many? Yeah, I heard it. I heard it.
4, because you got to add 1.
Oh, check. Who was it? Well, someone said it before. Go ahead. How many variables?
4,
4 variables because
you have to add 1.
you drew one from here to here, and it's going to touch that. That's why you got to do it first. You've got to do it first. So it's going to have an arc coming from 10 here. 1, 2, 3, 4. You ready? Every single node has negatives and positives. Not like shortest route, how the beginning's all positive variables and the end's all positive variables. This one's not like that. Every single node constraint is both positive and negative. You decide if you're making the ones coming in positive and the ones going out negative, or vice versa. That's up to you. You've got to be consistent for every one of these nodes. So that'd be 7 constraints. Let's make the ones coming in positive, I heard. What's coming into node 1?
7.
X7, 1 minus X 1, 2 minus X 1, 3 minus X 1, 4 equals 0. Now I made the one coming in positive, the ones leaving negative. Every single node constraint's got to be that exact consistency. If you start with positive and negative going out, you've got to be positive coming in, negative going out for every one of them. Want to do one more to make sure we get it?
Yep.
You ready? I'm going to do 4.
Oh, no.
I got to be consistent. Well, first of all, if I write the equal 0 on the right, I'm going to jam myself again. I'm going to start over here. I'm not going to put the equal 0. You ready? I'm going to stay consistent. Everything coming into 4, x1, 4 plus x2, 4 plus x, help me out, 3, 4? 3, 4 plus x, 6, 4? 5, 4, and it can be in any order, plus x, 6, 4. Is that true? 1, 2, 3, 4, 5 of them coming in. Is that right? You see 5 arrows hitting node 4 on the way in, yes? Let's do the ones way out now. Minus x 4, 2. Minus x 4, 3. Minus x 4, 5. Minus x 4, 6. Is that it? Or 7? Oh my God. Minus x 4, 7, thank you. Equals 0. Let me count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm starting right here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's it. You've got this all written down. You're going to forget this in 2 days. But if you can recognize a problem and go, oh, that's a max flow, jump to those notes, the little rules, start running your constraints if that's what it's asking for. And if you got that down, this is going to be so easy for you. I would put together a little, at the top, max flow, and then write those little rules down. Top, transportation, write the little rules down, just so you can go quick and not waste a lot of time. Because you need all the time you can get for the chapter 4 questions. You want to just zoom through chapter 6. I've made this so easy for you. I hope. I'm trying. All right? Are you ready now? The constraints for the arcs that you've never seen before, and this is only because the objective function doesn't have any of those numbers. Are you ready? For every arc is a constraint. So look at all the constraints we're going to add. It's not just those 7 node constraints. Now it's all the arc constraints. You ready? x1, 2 less than equal to 4. x1, 2 less than equal to 4. x1, 4 less than equal to what? 4. What's next? x1, 3 less than equal to? 3. x2, 4 less than equal to? 2. Everybody see where I'm going with this? So, because there's blankety blank number of arcs there, I should have that many constraints never, though, do the one you wrote. You don't have to do a constraint for the arc you added, because you added it just so it could be in the objective function, not a constraint. I want to make sure you see this. You ready? So watch, I'm going right here. All of those arcs are constrained. Right? X4, 6 less than equal to 1. If I go back and look at where 4 and 6 go, there'll be a 1 on it. X4, 5 less than equal to 3. X5, 4 less than equal to 4. Every arc is a constraint only for that last module, that last model. Here are all the node constraints. Let's check out number 4 here. Ready? Where's my positive? The ones coming in are negative on this example. The opposite of what we did, but negative x14, negative x24, negative x34, negative x54, negative x64. That's 5. We have it. Plus x42, plus x43, plus x45, plus x46, plus x47 equals 0. I hope this refreshes your memory. Like, you have a question on max flow, and you go here, and you go, oh, every node constraints equals 0. A very common mistake is, oh, it's like shortest route. The beginning is equal to 1, the end is equal to 1. And all the variables are positive at the beginning. Now that's shortest route. That's the difference between shortest route and max flow. You gotta be able to tell the difference. You know, I'll tell you what's scaring me. Is that I'm really emphasizing how to solve them, but I want to do recognition. You tell me, what kind of problem would this be if I turned it on? What? Hey, I couldn't see. Black screen. Okay. It's not turning on. I don't remember. Okay, here we go. Shoot. Going through 2 slots. And when they land on the back stream, they're expected to look like that. You know, just like a little light particle, but it's full time. But instead, they ended up looking like that, right there, as you send it up through. They didn't come out as just 2 structures. They were all over the place. You see that? Okay. What kind of problem is this right there? Not all at once.
Max flow.
Say it again.
Max flow.
No, John. No, you have to be right. I thought it was shortest route, but now that I stare at it, you're probably right. I think you're right. Max flow.
So why is it?
Well, let's take a look. A rental car company has an imbalance of cars at 7 of its locations. The following network shows the locations of concern, the nodes, and the cost to move the cars between the locations. The positive number of nodes indicates an excess supply at the node. And a negative number indicates an excess demand. So we have too many in demand here and not enough of supply. We have extra 3 here and up to 20 to be shipped, I guess. I don't know. See, I don't know how these numbers are going to come into play, but we'll see. All right, anyway. Is it max flow or shortest route? I still can't tell by looking at it. If it's shortest route, you rarely see these arrows on a shortest route. So, nice try, what? You don't know the answer?
Yeah.
Well, wait. Here we go. Hang on. I just thought of something. Let's look at what problems have been posted and have you recommend. Well, we run out of time here. You ready?
So that'd have to be a max flow, right? Because they're never coming back. So none of them from the center were coming back. It was only going one way, right?
That one was going in the
Three's going to 1.
Is it? Yeah.
Some can go back on max
Three's
flow.
going to 1.
Yep.
That's a tough one. This is tough.
Yeah. That was a terrible example.
Okay, you ready? Hang on. I want to go to number, this one right here at the top of the page. What's that? There we go. Who said it? Or probably it is. Too obvious? All right, let's try. And by the way, that's one of your homework right there. All right, the study problem. How's that? Let's try this one right here. It's right there. We got plants, it looks like we got warehouses, and we got capacity, and then we go warehouses here, the 2 warehouses here, going to the customers.
Transship.
There we go. Look at that though, see what's going on? Plants going to warehouses, the warehouses are going to customers. That you identify as a transshipping. It has a stop before it goes to the end. All right, let's try. This one, right at the top of the page, right there. What? Say, Sean? No. I appreciate you trying. No, where? Let's see. I heard it. Going from our southern and northern location gas companies to our end customers here. Here's how much we can provide. Or are those the demands? No, that's, oh, I'm sorry, here it is. Here's how much it costs. Our southern location can provide 500 units. Our northern location can provide 400 units. Hamilton is requesting 400 units. Butler wants 200 units. And Claremont wants 300 units. Transportation. Go ahead.
How many of these will be on the quiz?
I'm sorry?
Out of the 5 we're learning from, how many will be on the quiz?
I don't remember. I wrote the quiz already. I don't remember. I'm going to say minimum 2, maybe 3. You're not like doing the whole thing. You have a little part to do off one, and then you got another one to do a little part that's different. You know, it's not like, okay, give me the whole objective function and all the constraints of this one. Maybe just give me 2 constraints, this one and that one, or this one maybe just give me the objective function, the other one, you know. But you still got to be able to recognize them. That's the key. So you know what rules to use, even though there are a lot of similarities. Let's try. What was that over there? Let's try. You're almost like making it too easy because. Hang on, I got something's not right. What is that doing there? Is it on the wrong page? Oh, darn. I gotta get that answer down. The one that says number 7 is not the one I meant to post. No, it's not. Not that one. Hang on, let me find one that I meant to show you. Hang on, let me find one. Hey, there we go, number 17.
Assignment.
Actually, more left. Here's why it's assignment. We have 3 project leaders. We have 3 clients that need project leaders there. Here's some individual, could be hours billable, could be cost, it could be miles. You've got to decide whatever these numbers represent, maybe either minimize or max. In assignment problems, it's usually, I don't know if you go either way. I've seen a lot of maxes. Max advertising dollars, max billable hours, max, and then there's minimized mileage, because we have to reimburse the project leaders or something like that. In this case, what do those represent, those numbers? They're a accounting firm with 3 new clients. Project leaders will be assigned to these clients based on different backgrounds and experience of the leaders. The various leader-client assignments differ in terms of project completion times. This person would take 10 hours to do that based on, historically, this type of thing. 14 hours, 22 hours. Now, hang on a minute. The possible assignments and estimated completion times in days, those aren't even hours, those are days. Develop a network representing this problem and formulate a linear program to solve, but you don't know if to minimize impact, so you're going to have to literally imagine, you're working at an accounting firm that's got to assign project leaders, and the numbers are representing the amount of days that leader will probably take to take that project and get it done. Do you think those days maximize or minimize?
Minimize.
Wow, I heard a couple of maxes in a lot of minutes. Is that true? I think because most companies are trying to maximize revenue, that those hours represent billable hours. I think. A law firm for sure bills by the hour. And I think a lot of CPA firms bill by the hour also. And it's very possible that we want to maximize the bill by hours. So we would put Jackson, like on this obvious if this is on a quiz, whether it's a maximum bid. Won't be so controversial.
I'm not understanding why you wanted the math. What do you want?
The accounting firm bills the client based on per hour of the project.
Oh, okay.
And they wanna maximize revenue. So they wanna bill for as many hours as they
Also,
can.
they're going from CPA perspective, they want to.
Yeah, you're going from the perspective that this is your company, and
Oh.
you're trying to assign them, and you're greedy.
Okay, you're trying to.
Just like all law firms are. Greedy.
But maybe the company has like, this is a standard thing and we have this many billable hours.
And
so it's quicker to
that
do
would
it.
be exactly the opposite, where this is for sure minimize that. But I wanna tell you, if this were a real problem on a quiz, it will be obvious which way to go, where this one, but you're right, she's saying, when we build a client for the project, no matter how many hours it takes, then this is a miss. We want it to take us the least amount of time as possible, because as soon as that project leader is freed up, we can assign them to another project that will generate revenue. So in that case, absolutely. So this would either say, and the company bills per hour, and they want to get as much revenue as possible, we can say, they want to maximize revenue, just give it away, right? Or we'll say these projects are billed on a flat fee, and the company wants to have the least amount of time spent by the project, then it would get minimum. We feel pretty good? Are we good? Kind of a shorter lecture today, ready for the in-class?
Yeah.
Are we? Don't work a little bit. Get in, Chris, don't work a little, get moved in somewhere. Maybe you gotta move in somewhere a little bit, move one direction or the other. That's me, I'm looking
Oh, it's
here,
still recording.
and,